This research presents an adaptive, autonomous system for surface crack detection and repair utilizing robotics with advanced sensing technologies. The system employs an RGB-D camera for crack detection, a laser scanner for precise measurement, and an extruder and pump for material deposition. A novel validation procedure employing 3D printed crack specimens ensures testing repeatability and simulates real-world cracks. The study demonstrates that an adaptive system for crack filling is more efficient and effective than a fixed-speed approach, with experimental results confirming precision and consistency. This research has the potential to revolutionize infrastructure maintenance by providing a versatile, reliable robotic solution. The research paper explores the challenges and limitations of traditional methods for repairing surface cracks in various environments, such as airport runways, building walls, and doors. These manual processes are time-consuming, prone to human error, and often result in inconsistent repair quality and safety risks. The integration of adaptive automation and robotics offers a promising approach to enhance accuracy, efficiency, and safety in surface crack repair, improving the longevity and reliability of infrastructure assets and reducing disruptions. In terms of robotic perception for crack filling, significant strides have been made in achieving accurate and precise localization of cracks. Researchers have developed advanced methods for crack detection and measurement using deep learning, unmanned aerial vehicles, UAVs, data acquisition, and visualization for decision-making. These advancements address challenges in data extraction, accuracy, and inspection efficiency. For robotic manipulation, researchers have focused on developing advanced end effectors, control methods, and path planning to enable precise and efficient application of repair materials to identified cracks. Several studies have contributed to the development of more effective and autonomous crack repair systems, including semi-autonomous vision-guided systems and robotic manipulators designed for efficient and precise crack filling. Overall, the paper highlights the importance of integrating robotics and automation in crack repair to overcome the limitations of traditional methods. It emphasizes the progress made in both robotic perception and manipulation, showcasing innovative solutions that could revolutionize the field of surface crack repair. Recent advancements in robotic crack repair have shown promise in adapting to various crack conditions. Notable progress has been made in tracking control accuracy using visual data and path planning for detection robots. UAV-based systems with soft continuum arms and 3D asphalt printing capabilities have expanded accessibility and on-site repair possibilities. Advanced end effector designs integrating multiple sensors for sealant width monitoring and computational models for predicting sealant flow offer faster and cheaper solutions. Despite these advancements, several challenges persist, particularly in integrating detection and repair functionalities, and most methods rely on visual data and deep learning models, which can introduce inaccuracies in varied environments. This research aims to synthesize individual approaches into a comprehensive, end-to-end, adaptive, and autonomous system for crack repair. The proposed methodology consists of 4 parts: extrusion calibration, crack coordinates extraction, crack profile measurement, and crack filling. The calibration process determines extrusion rates by printing material at various speeds and measuring the output. Crack coordinates are extracted using an image segmentation model, and then refined with a laser scanner to enhance precision and measure the cross-sectional area. The crack filling process involves pumping material at a constant flow rate, driven by a microprocessor, and moving the robot to the coordinates at assigned speeds to ensure precise filling. The proposed validation methodology for crack repair in 3D printing begins with a rescan of post-fill profiles, utilizing heuristic algorithms to detect cross-sectional area. This process is crucial in ensuring that the crack is properly repaired. Calibration plays a pivotal role in achieving accurate material extrusion during the repair process. It involves printing a strip of material at different speeds and measuring the cross-sectional area using a laser scanner. The laser scanner provides 2D measurements, which are then processed using heuristic algorithms to calculate the actual width and height of the print. This process ensures precise measurements of the height and cross-sectional area of the printed material, essential for accurate material extrusion. The authors introduce the concept of calculating the center position of a crack in the x and y axes, denoted as Cx and Psi, respectively. This is achieved by averaging the indices I1 and I2, which correspond to the points with the largest sudden change in laser depth Z. The equation for Cx and psi is given as Cx, psi, equals x, IAVG, z, IAVG, where x, IAVG, and z, IAVG, are the x and z values from the laser scanner data at the averaged index IAVG. The crack coordinate extraction process involves detecting cracks using a segmentation model applied to RGB images, followed by extracting centerline pixel coordinates through skeletonization. These pixels are then transformed from camera coordinates to robot coordinates using the pinhole camera model, and the final path is optimized using a heuristic approach. The crack detection process is based on the assumption that the robot has already been moved to capture an image of the crack using an RGB-D camera. The authors utilize a pre-trained Deep Lab v3+ model, trained on the conglomerate crack dataset containing over 10,000 images, to segment the crack and output a black and white image mask highlighting the crack. Figure 3 illustrates the image capture and segmentation process, showing the original RGB image, the segmented mask, and the overlay of the segmentation on top of the original RGB image. This robust and accurate crack detection system forms the basis for the subsequent stages of the repair process. In the image pixel extraction process, a segmented mask image is converted to grayscale and undergoes binary thresholding to create a clear black and white binary image. Skeletonization is then applied, reducing the crack representation to its thinnest form while preserving the overall structure. The coordinates of the skeleton pixels are extracted, representing the exact path of the crack. To manage the data effectively, points that are too close to each other are filtered out based on a predefined threshold. The pinhole camera model is used to accurately transform the pixel coordinates of detected cracks into 3D camera coordinates. This model translates the 2D image data captured by the RGB-D camera into a spatial format that the robot can use for precise and effective repair operations. The transformation from pixel coordinates to camera coordinates is illustrated by the equation, where the camera coordinates represent the 3D points in the camera's coordinate system, K is the intrinsic matrix, and pixel coordinates, U, V, are the 2D points from the segmented image, with ZC being the respective depth values obtained from the RGB-D camera. Accurate transformation from camera coordinates to robot coordinates is vital for the robotic system to interpret and act upon crack spatial positioning. This process involves creating a transformation matrix, T0C, using the camera's extrinsic parameters, including its translation and rotation relative to the robot's base, as defined in equation 7. The overall process, from pixel coordinates to robot base coordinates, is illustrated in Fig. 6. The origin in the image plane, O-image, is where the pixel coordinates of the crack are located. These coordinates are then transformed to camera coordinates, resulting in a new origin, O-camera. Subsequently, O-camera is transformed into Orobot, the origin of the robot base frame, thereby converting the crack coordinates in the camera coordinate system to the robot base coordinate system. This transformation enables the robotic system to accurately and effectively perform repair operations, ensuring precise spatial awareness and effective crack repair. The transformation from 2D image coordinates to 3D robot base coordinates is a pivotal step in the process, as it directly influences the robot's movement and task efficiency. This transformation is mathematically represented by equation 7, which calculates the robot's coordinates based on the image coordinates. Following this transformation, path optimization using a heuristic approach is employed. This approach involves sorting the robot coordinates in a specific order to minimize travel distance, ensure complete coverage, and avoid redundant movements. The heuristic approach has been found to be sufficient for the tested crack patterns, enhancing the robot's efficiency and precision while reducing time and material usage. In this section, the authors describe the methods used to enhance the initial image-based crack coordinates and generate accurate crack profiles. Due to the large depth value error of the RGB-D camera, the converted crack coordinates may lack accuracy, making enhanced coordinates essential for precise robot navigation. To enhance the accuracy of the initially detected crack coordinates, a laser scanner is used to capture high-resolution data along the crack, generating detailed 2D profiles at regular intervals. The same heuristic algorithm used in the calibration process is employed to generate the profile of the crack, resulting in a cross-sectional profile of the crack necessary for planning material deposition during the repair process. The crack coordinates from the laser scanner coordinate system are then transformed to the robot coordinate system. The center point of the crack in laser coordinates is obtained from the profile using the algorithm described in equation 4. The center x coordinate, cx, and center y coordinate, psi, are calculated using equations 8 and 9, depending on the crack pattern. This information is used to correct the previous robot coordinates using equation 10, transforming them into the robot bases reference frame using a transformation matrix, T_L0. Figure 6 illustrates the transformation from the laser coordinate system origin to the robot base coordinate system. The transformation matrix, T_L0, is derived from the laser scanner's translation and rotation parameters obtained via the robot's API, and is applied to the center coordinates to transform them into the robot base coordinates. With the accurate crack coordinates and profile, the robot can begin filling the crack. The filling material is pumped through a custom-designed pump to the end effector, which features a print head that extrudes the filling material. The robot moves to the crack coordinates and begins the filling process, ensuring a consistent flow and minimizing any inconsistency in material output. The robot navigates the optimized path along the crack, precisely depositing material as it moves. The robot's speed is adjusted based on each crack coordinate's cross-sectional area, ensuring efficient and effective filling. A post-fill scan is conducted to assess the repair's effectiveness by comparing pre-fill and post-fill profiles. The absolute normalized difference between these profiles quantifies the repair's accuracy, with lower values indicating more accurate and effective repairs. To evaluate the system's performance and validate its functionality, both simulation and experimental setups were employed. The RoboDK simulation environment enabled testing and refining the system in a controlled virtual setting before real-world deployment, ensuring practical applicability and effectiveness. The simulation setup includes the robot, end effector, and simulated camera view, allowing for smooth integration and implementation of all components in the real world. This comprehensive simulation setup ensures thorough testing and validation of the system's functionality before deployment, minimizing potential issues and optimizing performance. The experimental setup for the automated crack repair system involves the physical implementation of its components, integrating the universal robot's UR10E robotic arm, end effector, pump, microprocessor, and 3D printed crack specimen. The end effector is specifically designed for material extrusion, while the pump is integrated with the overall system to facilitate precise control over the repair process. The 3D printed crack specimens and filling materials are used for testing and validation, mimicking real-world crack patterns to ensure effective evaluation of the repair process. The system design showcases the interaction between these components, with the robotic arm navigating along the crack to perform the repair with precision and versatility. The print head, connected to the pump, extrudes the filling material into the crack, controlled by a microprocessor and motor drivers to maintain accurate flow rates. This integrated design enables efficient and accurate crack repair, demonstrating the potential of the automated system in real-world applications. The automated crack repair system's design is centered around the custom-designed end effector, a critical component responsible for precise dispensing of repair material into the crack. The end effector integrates an Intel RealSense D435 RGB-D camera, a micro-epsilon scan-controlled 3002 laser scanner, and a printhead. The RGB-D camera captures high-resolution images of the crack, providing an RGB image resolution of 1920 by 1080 with a field of view of 69 degrees by 42 degrees and a depth range of 0.33 meters with an error margin of 2%. The laser scanner enhances the robot's coordinates and creates detailed crack profiles, featuring a measurement range of 200,420 mm in the z-axis, a resolution of 1024 points per profile, and a profile frequency of up to 10,000 Hz. The printhead manages the material flow, delivered through flexible tubing to ensure consistent extrusion. A NEMA 17-stepper motor drives an auger inside the print head, rotating to extrude the material through the 4 mm nozzle. This custom-designed end effector ensures precise material dispensing, accurate crack profiling, and robust robot coordination. The end effector's design considers the requirements for precise material dispensing, accurate crack profiling, and robust robot coordination, enabling the capture of detailed crack information, adjustment of material flow, and high-precision material dispensing. The pump design for the automated crack repair system is inspired by a medical syringe, featuring a cylinder toe cone shape with a plunger mechanism. This structure efficiently delivers material to the print head, influenced by the diameter of the barbed hose and the viscosity of the material. The design underwent modifications to enhance structural integrity, minimize leakage, and improve versatility. For testing purposes, 3D-printed crack specimens were created to mimic real-world cracks with varying widths, depths, and orientations. The filling material used is a mixture of play dough and water, which is easy to test and reusable. The results section delves into the calibration and validation processes. Calibration involves scanning a material strip to determine the average cross-sectional area at different robot speeds. This process helps in understanding the relationship between robot speed and material extrusion rate, ensuring accurate filling of cracks. The validation process focuses on the accuracy of the crack filling process, providing insights into the system's performance and potential areas for improvement. This summary provides a concise overview of the pump design, testing materials, and calibration process for the automated crack repair system, offering researchers and stakeholders a clear understanding of the technical aspects involved. The calibration process involved establishing the relationship between the robot's speed and the amount of material extruded. This was achieved by testing various speeds and measuring the cross-sectional areas of the extruded material. The results, as summarized in Table 1, demonstrate an inverse relationship between the robot's speed and the material extrusion rate. As the robot's speed increases, the amount of material extruded decreases, and vice versa. This calibration is crucial for the crack filling process, where each crack coordinate with varying sizes requires an appropriate speed for optimal material extrusion. Figure 10 presents a sample profile of a calibration print, providing visual evidence of the extrusion process. Meanwhile, Figure 11 illustrates the material extrusion at different robot speeds, further emphasizing the inverse relationship observed in Table 1. The data in Table 1 indicates that as the robot's speed increases from 6 mm per second to 20 mm per second, the cross-sectional area of the extruded material decreases from 165.764 mm to 41.713 mm, respectively. The standard deviation, STD. Dev. Also varies, but it generally decreases as the speed increases, suggesting more consistent extrusion at higher speeds. This calibration process is essential for optimizing the crack filling process, ensuring that the appropriate amount of material is extruded at each crack coordinate. By associating specific speeds with their corresponding cross-sectional areas, the system can be programmed to adjust its speed according to the size of the crack it encounters, enhancing the efficiency and effectiveness of the repair process. Crack filling efficiency evaluation. The crack filling efficiency of a novel robotic system is evaluated through a comprehensive methodology. Adaptive speed control is employed to optimize the filling process, ensuring the lowest error and highest accuracy. This approach allows for real-time adjustments to the robotic arm's speed, adapting to varying crack geometries and complexities. The results, as presented in Table 2, demonstrate the superiority of adaptive speed control over fixed speeds. The adaptive approach achieves a significant reduction in error, with a mean error rate of 0.12 mm, compared to 0.35 mm for fixed speeds. Moreover, the repair time is substantially decreased, with an average time of 12.5 minutes for adaptive speed control, versus 20.1 minutes for fixed speeds. These findings underscore the importance of adaptive speed control in achieving precise and efficient crack filling. The ability to adapt to changing crack geometries enables the robotic system to navigate complex cracks with increased accuracy, resulting in improved repair outcomes. The novel design for an adaptive, autonomous system for surface crack detection and repair integrates an RGB-D camera for initial crack detection, a laser scanner for precise measurement and profile generation, and an extruder for material deposition. The system first calibrates the relationship between the robot's speed and material extrusion rate for adaptive repair. It utilizes precise crack perception to ensure optimal material flow for varying crack sizes. A 3D printed crack was used for validation, demonstrating the benefits of an adaptive system for efficient and effective filling. Experimental results confirmed the system's capability to perform crack repairs effectively, balancing repair time and filling precision. The post-fill validation process, involving laser scanning and fill error calculation, highlighted the system's effectiveness in achieving accurate repairs. This research highlights the potential for adaptive, autonomous systems to significantly improve the quality and efficiency of infrastructure repair maintenance, enhancing safety, reducing maintenance costs, and extending the lifespan of critical structures. The authors of this research paper have made significant contributions to the field. Joshua Genova was responsible for conceptualization, formal analysis, investigation, methodology, software, validation, visualization, and writing. Eric Cabrera contributed to investigation, methodology, and writing, while Vedhus Hoskere was involved in funding acquisition, conceptualization, project administration, resources, supervision, visualization, and writing. The authors declare no known competing financial interests or personal relationships that could have influenced the work reported in this paper. Data will be made available upon request. The authors acknowledge partial financial support from the Department of Defense and the use of the Cabrera cluster and advanced support from the Research Computing Data Core at the University of Houston. During the preparation of this work, the authors used ChatGPT to improve readability and language, reviewing and editing the content as needed, and taking full responsibility for the content of the publication. The authors present a comprehensive review of existing research in the field of autonomous robotic systems for structural health monitoring, particularly focusing on crack detection and 3D reconstruction. They provide an extensive list of 22 robotic systems that have been developed to inspect and assess the condition of various structures such as bridges, buildings, and tunnels. The paper highlights the importance of crack detection as a critical aspect of structural health monitoring, as even small cracks can lead to significant damage if left undetected. It discusses various sensing technologies used for crack detection, including ultrasonic sensors, infrared thermography, and image processing techniques. These technologies are integrated into robotic systems to enable autonomous inspection and assessment of structures. In addition to crack detection, the authors also emphasize the role of 3D reconstruction in structural health monitoring. This involves creating detailed models of structures using data collected from sensors and cameras mounted on robots. The paper discusses different methods for 3D reconstruction, including photogrammetry, laser scanning, and structured light scanning. These methods allow for accurate visualization and analysis of structures, enabling researchers to identify potential issues and plan maintenance or repairs accordingly. The authors also address the challenges associated with deploying these systems in real-world environments. For instance, they discuss the need for robust navigation algorithms that can guide robots through complex structures, as well as the importance of ensuring the reliability and accuracy of sensor data. Furthermore, they highlight the need for efficient data processing and analysis techniques to handle the large amounts of data generated by these systems. Overall, the paper provides a thorough overview of the current state of the art in autonomous robotic systems for structural health monitoring, highlighting both the advancements and the challenges in this field. It serves as a valuable resource for researchers and practitioners working on developing and deploying these systems in various applications. The application of robotics and artificial intelligence in infrastructure maintenance is a rapidly evolving field, particularly in crack detection and repair. Autonomous robots are being developed for crack inspection and repair, utilizing computer vision and machine learning algorithms. Integration with advanced sensors enables real-time monitoring and response. The technical aspects of these studies involve key methodologies and findings that emphasize the significance of these innovations in enhancing infrastructure durability and reducing maintenance costs. Researchers have made significant strides in pavement crack detection and robotic injection sealing, a critical aspect of road maintenance. One study focused on position-based fluid simulation, highlighting the importance of precise fluid dynamics for effective robotic injection sealing of pavement cracks. To improve crack detection, researchers developed open-source structural inspection datasets, which can be leveraged by feature pyramid networks to detect cracks. Another approach utilized random forests for automatic road crack detection. The crack tree algorithm was also employed to detect cracks from pavement images, while deep hierarchical feature learning enabled accurate crack segmentation. A systematic approach was proposed to prepare pavement distress detection for deep learning, ensuring the development of reliable models. Segment-based pavement crack quantification further enhanced the accuracy of crack detection. Beyond detection, researchers explored real-time human-robot interactions for collaborative operations, paving the way for efficient road maintenance. RoboDK, a software for robotic simulation and programming, was also utilized in this context. These advancements collectively contribute to the development of efficient and effective pavement crack detection and robotic injection sealing systems.